So now let's begin discussing the derivative. So here is how we are going to define the derivative. Very first definition, section 2.2. So let's let our domain X be a set of real numbers, and let's let some point A be, it has to be both a point in X and it has to be a limit point. Of X. So remember, we said to be in the closure you had to be either in X or a limit point of X, but not necessarily both. Well, to be differentiable at A, you have to be both in X and a limit point of X. And let's let F be a function whose domain is X. And then we define the derivative of f at A that's given by, and some of you may have seen this definition in high school. Well, I did. If you didn't, that is okay. We write f prime of A. That is the limit as X approaches A of this quotient. We write f of X minus f of A over X minus A. Yeah. And remember that our statements of limits cared very much about the domain. So let's note that where the domain of the thing we're taking the limit of, that is taken to be the set X, and then you delete the point where you're dividing by 0, and so that quotient is not defined. So let's take the usual example of this, our pictures. So here is the graph of a function. Here is our point A. Then here, of course, is f of A. Then what you do is you take a point X, you go up to f of X, then you draw the straight line that goes through f of A and f of X. And then as X gets closer to A, this line is going to get closer and closer to the tangent line at A. And it's the slope of the tangent line that is the derivative of f at A. And I want to emphasize here in this particular example, our domain is not all the real numbers, it's a closed interval. So you are allowed to decide you want A to be an endpoint. Now in the example on the right, your secant lines, that's the points that go through both f of A and f of X, they are getting closer to the tangent line in from both sides, but for our endpoint here, your points X are approaching from one side, your tangent lines are approaching from one side. That's okay. That's just giving you a one-sided limit. And in practice, derivatives are pretty much always of functions defined on intervals. So generally, that's the only kind of domain you have to worry about. So here is an important result about differentiable functions. Let f be a function that goes from a domain X to the real numbers, and A is in X. And suppose that f is differentiable at your point A. And that means that A is a point in X, A is a limit point of X, and f prime of A, that's the limit as X goes to A. Remember, limits don't always exist, but so when we say f is differentiable at A, we mean that limit exists. And the conclusion is that if you're differentiable, then you're continuous. Then f is continuous at A. The reverse implication is not true. There are all kinds of continuous functions that are not differentiable. The absolute value function is continuous but not differentiable at 0. The square root of X, it's continuous but not differentiable at 0. Lots of functions like that. But the reverse implication is true. Let's prove this. So first I'll point out that these two limits exist. That limit is f prime of A, and here's another limit we're going to need. It's the limit as X approaches A of X minus A. And I'll point out that both of these limits exist. And therefore, we can use proposition 2.1.5. So by proposition 2.1.5a, we have that the limit as X approaches A, f of X minus f of A over X minus A times X minus A. So proposition 2.1.5, sorry, this is part B, it says that if each of the two pieces has a limit, then the product also has a limit, and the limit of the product is the product of the limits. So this limit is in fact 0. So then just doing a little bit of algebra, the thing we're taking the limit of now, our new piece, that is equal to our old piece everywhere except at the point A. Our new function is 0 at the point A. Our old one is undefined. And we noted last time that if you've got two functions that match everywhere except at A, then their limits at A have to be equal. All right. Now, I'm going to notice that the limit as x approaches a of f of a, any constant function has limits everywhere, and f of a, that's a constant. You think of this as for the function that for all x spits out f of a. So I know it doesn't look like a constant, but we're letting x be variable. We're fixing a. So f of a is a constant. So by proposition 2.1.5a, we've got that the limit as x approaches a of f of x minus f of a plus f of a, that has to be since the two summands have limits, the limit of the sum is the sum of the limits is f of a. And then notice that our first piece, this is the limit as x approaches a of f of x. Since the two things we're taking limits of are f of x and this complicated difference, those are equal not just at everywhere except at a, they're equal at a too. So we've got that the limit as x approaches a, f of x equals f of a, and then so by corollary 2.1.3, if the limit as x approaches a, f of x equals f of a, f is continuous at a. Now we're going to go over the usual rules for derivatives. I'm sure you all will know these. These tend to be taught very well in freshman calculus and any calculus course with a lot of future engineers in it, which is most of them. But we're going to go ahead and prove that these work. Let's let A be a point in our domain X. F and G are both functions with domain X. And F and G are both differentiable. At A, meaning A is a point in X and a limit point and the limit of the difference quotient exists. Then we've got the following three things are true. First is the sum rule. F plus G is differentiable at A. And the derivative of the function f plus g at a, that is just f prime of a plus g prime of a. And the same thing is true for products. Except that we've got the usual complicated product rule that you all know and love. And last of all, we have the quotient rule. If g is a function from x to r minus 0, that is, g of x is not allowed to be 0 for any x in our domain, then the quotient is differentiable. At a. And if there are a few isolated points where g is 0, you can just throw them out of your domain, and as long as a isn't one of the points you throw out, that is, as long as g of a isn't 0, then your function is going to still be differentiable at a. And we have our usual quotient rule, f over g prime of a. That's f prime of a, g of a. Then we subtract off f of a, g prime of a. And we divide the whole mess by g of a quantity squared. So let's prove this, or at least we'll prove parts B and C. Part A is pretty straightforward. Maybe that will be a good exam problem. So first thing I want to point out is that by proposition 2.2.4, we're assuming that f and g are differentiable at a. We're assuming that f prime and g prime exist. So proposition 2.2.4, f is continuous at a. So by corollary 2.1.3, we have that f of a, that is equal to the limit as x approaches a of f of x. So let's write this down. We're going to write f prime of a, g of a, plus f of a, g prime of a. F prime of a, by definition, is the limit as x approaches a, f of x minus f of a over x minus a. And then g of a is a constant. We discussed this in the last proof. I'm going to go ahead and write that as the limit as x approaches a, g of a. And then by what we said before, our f of a is the limit x approaches a, f of x. And then we've got the limit as x approaches a, g prime of a is this different quotient. And notice and all four limits exist. The limit of g of a exists because it's a limit of a constant. The limit of f of x exists by proposition 2.2.4 because f is continuous. And the limits of the difference quotients exist because f is differentiable at a, g is differentiable at a. That means the limits exist and equal the derivative. Then, because the limits exist, because we know the limits exist, we can apply proposition 2.1 and 0.5, first b and then a. We can rewrite this that as one big limit. So first we use part B to consolidate the products, f of x minus f of a over x minus a times g of a. And we do the same thing with the other piece. And then by proposition 2.1.5a, the limit of the sum is the sum of the limits. And then we can simplify the inside a little bit. I'm going to distribute this g of a in f of x g of a minus f of a g of a. Then we add to that g of x, f of x, minus f of x, g of a. And then notice that the entire thing is divided by x minus a. Then the next thing to notice is that, oh look, we've got f of x minus g of a here, f of x minus g of a here. They cancel, and we can write down this very simply as the limit as x goes to a, f of x, g of x, minus f of a, g of a, over x minus a, and the limit exists. And we recognize that that's the difference quotient for the function fg. So fg prime of a, limit as x goes to a, fg of x, which is the same thing as f of x g of x, minus fg of a, all over x minus a exists and equals the thing it's supposed to be, f prime of a, g of a, plus f of a, g prime of a. Now let's go ahead and prove part C. The algebra is going to get a little hairy on this one, but that's okay. So let's write it this way. F prime of a, g of a, over g of a squared, minus f of a, g prime of a. So that whole thing is, we'll say that it is equal to, so f prime of a, that's the limit as x approaches a, f of x minus f of a over x minus a. And then let's go ahead and leave the g of a as a g of a. Then we'll subtract off, leave the f of a as it is. And then I think I'm going to, for reasons that will become apparent, I will leave one of the g of a's as a g of a and then turn the other one into the limit as x approaches a g of x. And then at this point, it should be clear to everybody that I'm allowed to just move constants inside of limits if I want to. So we rewrite this whole mess as limit, our denominator becomes the limit as x approaches a, g of x, g of a. Our numerator is the limit as x approaches a, f of x minus f of a over x minus a, g of a. Then we subtract from that the limit as x approaches a, g of x minus g of a over x minus a, and then we've got an f of a out front. And notice that all three limits exist. Then we combine the top two, the sum of the top two. Let's leave the denominator alone for just a moment. And then we've got f of x. I'm going to go ahead and move the g of a in. And then the other piece, minus f of a, g of x, plus f of a, g of a. Okay, boy, what a mess. This is true by proposition 2.1.5a, because we can combine sums. We've got some cancellation going on here again. And our f of a, g of a, and f terms cancel out with each other. And now what we're going to do is we're going to use part C of 2.1.5. Now, g is not allowed to be 0 anywhere. And we assume everyone remembers how nested fractions work. We get an x minus a g of x, a g of a, f of x, g of a, minus f of a, g of x. And then I'm going to go it, and then we do just a little bit of algebra. And then we can cancel all some powers of some g's here. We're left with the limit as x goes to a. F of x over g of x, I'm going to write that as f over g of x minus f over g of a, x minus a. And then, so that is exactly the derivative of f over g. So f over g prime of a is equal to the horrible thing up here given by the quotient rule, and in particular, it exists. So f over g is differentiable at a. All right, let's have an example. This is example 2.2.6. This is going to show that the derivative of a polynomial, we're going to prove that it's the thing we saw in calculus. So first off, if f of x equals c for all x, where c is constant, then this limit as x grows to a, f of x minus f of a over x minus a, that's the limit of as x approaches a, c minus c over x minus a. And that function is 0 except when x equals a, and the limit of a constant is itself. So f prime of a equals 0 and exists for all a. So the derivative of a constant is a constant. You all knew that, but that's not too surprising. So now, if g of x is the identity function x, then limit as x approaches a, g of x minus g of a over x minus a, limit as x approaches a, x minus a over x minus a, that's equals 1, so g prime of a exists and is equal to 1 for all a. Note that we can write this one as 1 times a to the 0 because after all any number to the power of 0 is just 1. So now we're going to get the power rule that you know and love. So suppose, so let's let hn of x be x to the n. Suppose that hn prime of a equals na to the n minus 1 for all a, and in particular exists. And then the difference quotient hn plus 1 of x minus hn plus 1 of x, then actually we're going to write it like this. We're not going to bother with the difference quotient hn plus 1 of x. That's hn of x times our function times g of x. G of x is x in the last example. So hn plus 1 prime. Hn and g are both differentiable, so hn plus 1 prime exists, and it equals hn prime of a, g of a, plus hn of a, g prime of a, and if you work out what all those come out to, you end up with n plus 1, x to the n, a to the n. Then by induction, if hn of x equals x to the n, then hn prime of a is a to the n plus 1 minus 1, for all natural numbers n. Base case is our g of x equals x, also known as h1 of x equals x to the first equals x case, and we just saw that it's true by induction. And then last of all, if p is a polynomial, p of x is some constant plus some other constant times x plus some constant times x squared up to some constant times x to the k then p prime of, well, I really don't want to call it a now, I'll just say p prime of x. That's sum from n equals 0 to k. The an, the constant hangs out front. The derivative of a constant is 0. So when we apply the product rule here, we get an times our nx to the n minus 1. And the part that involves the derivative of an, that's just 0. So that you can write this as a1 plus 2a2x, and so plus up to k ak x to the k minus 1. So the conclusion here is that all polynomials are differentiable, and the power rule that you remember from freshman calculus also works.